Hi everyone, it's time for another space failure analysis, this time for Japanese lunar lander which is called SLIM. The SLIM lunar lander encountered an anomaly during its descent. While the official investigation into the incident is ongoing, it's valuable to consider some hypotheses for potential reasons behind this event. These reasons can provide insight for the interested individuals and startups in the field of space exploration. After SLIM successfully landed on the moon, officials released an image revealing a concerning sight. A nozzle from one of the engines and three shining objects had broken off and fallen to the surface during descent. This unexpected occurrence raised questions about the integrity of the spacecraft propulsion system and prompted an investigation into the incident. To grasp why the nozzle detached from the SLIM lunar lander during its descent, we must first gather all available information concerning the incident. With the additional insight from the officials' report regarding the telemetry data, we now have a clear timeline of events surrounding the detachment of the nozzle. At 1918, an abnormality in the engine was observed at a height of 50 meters above the lunar surface. Just 2 seconds later, at 1920, the nozzle was observed on the surface of the moon, indicating that it had detached from the lunar lander and fallen during this short time frame. With the kinematic equation, we can determine that the initial velocity of the nozzle was indeed 26.6 meters per second. However, it's crucial to note that this velocity doesn't align with the free fall conditions. While it's possible that such a velocity could result from an explosion, but it is not the only possible explanation for that. Other factors such as mechanical failures, structural weaknesses, or sudden propulsion system malfunctions could also lead to the ejection of the nozzle at this velocity. Telemetry data for engine thrust and velocity is also available. But let's continue our analysis. We will circle back to the telemetry data for the engine thrust and velocity at the end of this video. Additionally, I did some searches using Japanese keywords to gather more information about the engine. Looking at the control diagram of the engine, one can observe potential areas for leakage. But as the design of SLIM prioritizes lightweight construction, the main structure consists of a tank with other instruments connected to it. While any leakage in the valve could result in catastrophic failure as it connected to the tank, SLIM managed to land safely. Thus, leakage is less likely to be the source of the nozzle failure. I also found another document detailing the assembly of SLIM. It reveals a separate structure for the area where the nozzle are located, distinct from the tank and other components. This shows an issue were to occur only in the nozzle area, it would not propagate through the entire lunar lander, potentially ensuring the safety of spacecraft. There are two identical engines in the middle, so why did only one engine's nozzle experience detachment? It has been revealed that this particular engine was fueled with less fuel and more oxidizer. Scott Manley mentions in his video that oxidation of the nozzle could potentially cause it to shear off. This phenomenon has occurred previously with another Japanese satellite, Akatsuki, during its journey to Venus. I highly recommend watching his video. The link is provided in the description. The next document I came across details the manufacturing history of this nozzle. Firstly, it reveals that this nozzle is the same as the one used for Akatsuki satellite. Secondly, it indicates that this particular nozzle does not have a coating resistant to oxidation. This is due to the decision to increase the combustion temperature by 200 degrees Celsius, with the claim that oxidation-resistant coating is unnecessary. It appears that the same mistake may have been repeated, potentially leading to the nozzle detachment issue experienced by the SLIM lunar lander. However, there remains an unanswered question. The fracture due to the oxidation typically involves gradual crack growth and does not result in sudden ejection of the nozzle toward the surface. Let's explore another aspect of SLIM. Its ambitious mission goal to land on the moon with an accuracy of 100 meters compared to the 10-kilometer accuracy of previous mission. This represents a significant advancement in lunar landing precision. To achieve this level of accuracy, SLIM employs autonomous image processing technology. This system analyzes images of the surface, compares them with the previous images it has stored, and makes a real-time decision about the landing location. Such precision requires a highly maneuverable lunar lander. This maneuverability is achieved through the development of high-firing performance engine and flexible pulse operation capabilities. These features enable SLIM to adjust its thrust output by freely combining on and off times, allowing for precise control over its descent trajectory. I think as the oxidation starts to create cracks in the nozzle, the stress within the material increases. Subsequently, the impulsive on and off operation of the propulsion system could have exacerbated this stress, ultimately leading to the detachment of the nozzle and its subsequent ejection toward the lunar surface. Now let's delve into the potential explanation for the 3 shining objects observed during SLIM's lunar landing. But first, don't forget to like, subscribe, and share your thoughts in the comments about what you think these shining objects might be. SLIM has 12 thrusters, 3 on a row for each side. Comparing the post-landing image of SLIM with its 3D model reveals that a row of thrusters is missing. At a height of 50 meters, with the tank nearly empty, one engine alone was sufficient to counteract the moon's gravity. However, with 12 thrusters, SLIM should have been able to maintain a stable descent posture without nosing down. The absence of thruster nozzles on one side may have resulted in a lack of counterforce, leading to an imbalance. It's possible that the nozzles of the thrusters are made from the same materials and manufactured using the same process as those of engines, making them susceptible to oxidation. Assembly documents indicate that the thruster nozzles are delicate and prone to bending even with minimal force. Combined with the high impulsiveness of control system, it's conceivable that cracks and breakage of the thruster nozzles occurred similarly to those of the engine nozzles. One final point to consider is the arrangement of the 3 shining objects in relation to the engine nozzle on the lunar surface. While the thruster nozzles typically align in a row, the observed objects are positioned on the left, top, right sides of the engine nozzle. This discrepancy suggests that the initial velocity of the objects may have had 2 directions, not solely directed toward the ground. To confirm this hypothesis, telemetry data could provide valuable insights. However, the telemetry data I've accessed indicates that at some point, the engine power value reached 440%, which seems inaccurate. As a result, I didn't use this data for analysis, since it is unreliable. Hopefully, in the official investigation, authorities have access to the precise location of sensors and can utilize this data to justify and analyze the trajectory of the objects more accurately. This will help in uncovering the true nature of the shining objects observed during the SLIM lunar landing. In the space industry, encountering failure is almost inevitable, and it's often said that if you are not failing, you are not pushing the boundaries enough. However, the key is to learn from these failures and ensure that mistakes are not repeated. It is surprising to see that the issue with the nozzle manufacturing wasn't addressed or overlooked after 14 years. Nevertheless, I remain hopeful for the Japanese lunar lander's next attempt, and I wish them a safe landing. Thank you for watching this video, and I will come back with another video in space failure analysis.